right, boys and girls, get done. Let's go. Get those problems from 4.5 out, please. They are also located in this week's folder, in case you're looking for them. Is everybody in the right seat? I think so. Some of you didn't move, some of you did. I'm supposed to move. No. I just kind of. I had to remake my seating charts to accommodate somebody who isn't even going to be in class for the next 2 weeks. So. I'm kidding, okay. We do have 3 remote learners this time around, so if I'm playing with stuff up here, it's because I'm trying to get that organized. All right, like I said, when you're done, get your problems out. We're going to start.
I definitely submitted the 4.5 problems. I submitted the one we did on the Zoom call. Like the one problem we did. So,
Yeah, they're just in the module.
yeah.
I love this.
I found my good pencils in my desk. I wasn't using an online tool, and I was like, these.
I haven't used one of those pencils in so long.
I know, I always use the like colorful like skin.
Me too.
All right, who's here? Who's not here? I appreciate that. I appreciate that.
Really online?
Yeah.
She better come back. She better come back.
I'm sure she will. You don't think she will?
She really said.
When you say come back, do you mean like in person?
Yeah.
Oh. All right.
That was funny.
Cool. That was scary. Oh crap! I forgot to hand out something last hour. All right. We're gonna start with number 1 on the tug of war, and the reason I want to go through these is because I need to make sure we understand free body diagrams. I know that these are rough, but one of the things that we want to talk about is how they're typically drawn, and there's 2 major ways. You'll have seen them both ways. One is typically the point mass, and the point mass is the most common of them. It means we put the massive or the system down to a single point on a grid. In this particular case, we would draw all of the forces acting on that particular object. Right? Imagine this is our box on a table. Okay? The other way you see free body diagrams drawn is just as a function of the diagram itself. Okay? Please remember that normal always acts perpendicular to a surface. That was one of the videos that I sent you. We have a person sledding down a hill. The angle at which this person is sledding is going to have to do with a couple of different things. We're going to have some forces that we have to look at in this particular sense. If we take this particular diagram or this situation and we move it over to a free body diagram, it may be your impulse to draw things the way that you see them in the diagram. What I would prefer you do is you turn the diagram so that you can see that forces are on the axes as much as possible. If I take this and I turn it, it looks like this. We did this in the video. I don't know if you remember this, but the angle that the weight vector plays on is exactly the same as the angle of the slope that it's on. So all I did was take this one and rotate it so that normal and friction were on the y and x axes respectively. What's the next thing I would do with this particular type of situation? Does weight at 25 degrees help me at all? No. What should I break it down into? W perpendicular.
Oh, and parallel.
And W parallel, right? This one would be parallel. And this one would be perpendicular. When we say parallel and perpendicular, we mean to the x-axis. Okay? When I do that, my free body diagram changes again. To become that. Okay? When we write out F net, right, and when we're trying to adjust our free body diagrams to an equation form, I do want to remind you that we can have it in both directions. You can have F net in the x and F net in the y. Whichever direction this motion is actually occurring, that F net is going to be the one that does not equal 0. If there is no movement in one of the two directions, say in the y direction, nothing is moving, then we would say that F net equals 0. Does that make sense? So remember that an object has to be moving and changing motion in order for it to have an acceleration, which means that F net will only equal 0 when the object is not moving in one direction or when it's moving in a constant way in one direction. Okay? As this person slides down this hill, are we assuming he speeds up? That makes sense, right? If I roll a ball down a hill, isn't it going to get faster and faster and faster up to a certain point?
Yeah.
Absolutely. So, in the y direction, his F net will equal m times a. Or, I'm sorry. M times a, right? We're saying he's moving in the x direction. Remember, we turned this diagram. We're saying this is the x direction is down the hill. Okay? Is he moving in the y direction? Is he jumping up and down as he runs down the hill? No, he's not. So the y direction is going to be the one that has 0. Now, how do we take the diagram and use the forces in a diagram? Remember we said that anything to the right is positive, anything to the left is negative, anything up is positive, anything down is negative. So, in the x direction, we can write F minus W parallel. In the y direction, what can we write? What's positive on this diagram? N minus what's negative? W perpendicular. Okay, so now this is how we get those expressions that we were seeing in those videos. What does this one tell me? Could you solve for normal? You could. If you knew the value of W perpendicular, could you tell me what normal was? Yeah, this relation says this, right? This one, could we solve for friction if we didn't know friction and we knew everything else? Yes. Could we solve for A if we didn't know anything else? Or if we knew everything else, I mean? Absolutely. And this was one of those problems that we did in a video. Okay. We good? Free body diagrams. Those are coming at you. 4.5 is the cutoff, I think, for your final exam. We have quite a few things that we need to go over. Moving backward from when we were remotely learning. This being one of them. And we'll be working with some of these forces in the next few days using labs. So, fair warning. 4.5 is the cutoff for your final exam. All right, the first question on the 4.5 practice problems that you were given has two teams of 9 members each. You've got team 1 and team 2. You're told that team 1 has, each member has an average mass of 68 kilograms and a force of 1350 newtons. Team 2, you were told, has a mass of 73 and a force of 1365 newtons. If you draw yourself a diagram, we're going to put a mass system in the middle. We're going to assume that the system contains all 18 members in the rope that they're pulling on. That means you've got 9 people pulling in one direction, and you've got 9 people pulling in the other. Direction. That's a lot of arrows. Let's say team 1 is pulling this way to the left, and team 2 is pulling to the right. What other forces do we have at play?
Wait.
W and N. Are we assuming W and N are straight up and down? Yeah, because we assume they're pulling on a level ground. All right. Now we want to know what is the acceleration. So what is F net in the y direction? There are 2 answers here. What are they? What else?
N minus W.
Thank you.
Perpendicular.
N minus W. What else? So for F net x, what do we have?
N times A.
Yep. And
F minus W.
we've got F2 times 9, if you will, minus F1 times 9. Which of these 2 equations is going to help us get an acceleration? The first one. Should be able to solve from there, I hope. What's the mass in this?
Do we add both of them or
Oh,
subtract?
you're going to add them all times 9, remember? So you're going to do 68 times 9 plus 73 times 9 to get your total mass. Then you're going to solve for A. It's an A, not a 9. you know where my calculator is? It's been a while. Ooh, it's gonna be a small acceleration. All right. Is that a very small number? 0.1, about a tenth. The tension in the rope between the two teams is just going to be the net force. All right, so that was number 1. What other problems do you want me to go over? Can we do number 3? Okay. Ooh, the 60-kilogram gymnast climbs up a rope. What do we know about a rope with a mass suspended? What are the forces at play? What's this one? Is it in contact with the surface? No. So what is it instead? Tension. And then the person has a mass, right? Which means weight, which is mg, of course. You're right. Okay. It says A, what is the tension in the rope if they climb at a constant speed? Ooh. What's my F net expression here? It would be T minus W, right? That's the expression. What should it equal if we're at a constant speed? 0. What should it equal if we're accelerating? F net equals Newton's second law, ma. Which situation are we dealing with in part A? Correct. So in this one, T equals W, and we do have W because it's mg, right? We know that the person weighs 60 kilograms, so we're going to do tension equals 60 times 9.8. Well, that was one of the big concepts here in this chapter was tension equals weight when it's just hanging. When an object is just hanging at constant speed or not speed at all.
Because the first one is real in my head. Like, I went completely wrong direction.
All right, so there's that one. In part B, it says, what is the tension in the rope if this person climbs at a rate of 1.5 meters per second squared? In other words, what happens if A is 1.50 meters per second squared instead of not there? So here we're going to do T minus mg, which is weight, remember? This is A, this is B. Equals guy is 9.8. What are the masses? 60. So tension will equal 60 times 1.5 plus 60 times 9.8, which will equal 678 newtons. The difference here is constant speed versus not moving at all are the same exact ideas, same exact situations. Yes?
Would it be wrong to do like tension equals, and then I did the equation M and then parentheses A plus G.
It's the same idea because the mass is just,
So that could be correct too.
yeah, because you just had mass, right?
Yeah.
Did we understand the tension in the trampoline? Yeah. Yes. Do we understand tension in tight ropes and in trampolines? Feeling good about that? Okay. Let's do some more. One second. Gonna find us some angle problems, which I'm sure you're excited about.
I
How are we feeling being back at school?
feel like I'm more school focused.
You're more focused?
Yeah, than I am. Yeah.
That's fair.
Like online is nice, but like.
For the lectures at least.
Oh yeah.
That's
Yeah, easier in person than it is anywhere else. I want something at an angle. Oh, yes. We're going to do the children on the snow saucer. Got excited. Does anybody know what a snow saucer is?
like one of those little things.
Like, you ever tried to slide down a hill on like a trash can lid? Like a circular one? It's a saucer. All right, so 2 children pull a third child on a snow saucer, exerting forces. So here's the person. This is the child on the saucer. We've got one person exerting a force here. We've got one person exerting a force here. Did I get that right? Nope, that one's 45. So it's 30 degrees. Find the acceleration of the 49 kilogram sled child system. F1 is 10 newtons. F2 is 8 newtons. The frictional force angle unknown. But the frictional force is known to be 7.5 newtons. Okay?
No, this is
We're doing a problem.
Sweet.
We're just attacking a problem. Okay. So, our free body diagram is going to look very wonky, right? We can do some stuff to change our free body diagram, but let's start with the base model. Okay? What are we going to put first? What do you think? So we are looking down on this child, okay? We're like helicopter viewing the child on the ground, okay? Does that help?
Yeah.
All right, so what forces are we not going to have in our diagrams?
Weight.
And
Normal.
normal, because we're looking down, we're not looking side on. You remember the conversations that I tried to have with you virtually about inertial frame of reference and how you are looking at a situation versus how the situation's actually playing out. In this particular case, what we see matters because it means there aren't going to be some forces that we have to deal with. Okay? All right, so there will be no normal, and there will be no weight force. Does that mean the mass of the child doesn't matter?
No.
No, because we still have F net equals MA, right? So formulas we might need on the right. Weight equals mg, probably not, but still, formulas that are really most common that we need to know. All right, so we've got these forces. We've got F1, we've got F2, we've got friction, though we really don't know what the angle on friction is. We're just going to put it in our diagram for now. Okay. We do know angles here. And what else do we know here? We know their actual numbers. The more information you can put in a diagram, the better off you are. Okay. So since these are on an angle, what do we know? What can we do?
Vector.
Oh, it's a vector, right? Does it have an x and a y component? It does. You're going to see me start using things like F1x and F1y. I'm going to do the same thing for F2. Just going to draw my diagram. 2y, F2x. What we need to do first, and this is our approach, if you will, we need to figure out what the final resultant vector is. Because this will give us the angle on friction. Remember that friction has to act opposite of whatever that resultant vector is. So we have to add our two vectors together, and we've done that over and over this semester. First thing we're going to do is we're going to break them into our components, right? We're going to figure out what x's and y's are using our trig. Then we're going to add the x's together, we're going to add the y's together, and we're going to get a resultant vector from those two different parts. Okay, so let's start with F1. The angle is here. SOHCAHTOA. So is opposite. So sine would be our y, right? Opposite over hypotenuse. That means that. Over here, opposite's also still going to be sine. So F2y all right, get it worked out on your calculator. I'm going to turn the heat off. I'm dying. It's been home for like 6 days. What should your calculator be in?
Degrees.
Yeah.
What does it say? It says gives us blank on that.
Angle. All right, go ahead for F1y.
7.07. And then 7.07 for the next.
Oh, yeah.
Then 4. And then 6.91. No, 3. 6.92.
let's check to see if you calculated
It
it
is.
wrong.
32.
Oh, you have to do F1 and F2. F1 is the 10 newtons and F2 is
Oh.
Come on, kids. Okay.
Oh, did this next seed?
It's 14.45 and then 10.13.
14.14? Then you're doing theta and r. Once you have these, the next thing to do is to figure out what the total x and the total y approaches are. So you're going to add all your x's together, add all your y's together to get your resultant x's and y's. Yeah.
I think I did it wrong.
Which one?
I did 7.07 plus 7.07, so it should be 7.07 plus 4 for X.
Oh, right. Okay. Okay. So what's that one?
That should be 3.06. No.
11. So that one should be 11. Nope, that's the other one.
Yeah. And then
This one should be 11.07. The y's.
yeah, and then it should be 14.
Okay. So then you do r and theta r. Whatever r is, friction has to go opposite because that's like our net force vector. That's our goal. Our ultimate goal is to figure this part out because once we have this, we can just move on to Newton's second law. Who has r? Who has theta?
I got 17.85 for Sweet. I didn't do theta yet.
I did theta. I got 30.33.
Okay. That sounds kind of high, but
I got 38.33 too.
I got 37.7.
you got 37.7? It's close to 38. Probably rounding. Okay. But we are in mostly agreement that it's somewhere in the 30s.
Yeah.
Okay. So that means that R has an angle 37, 38, whatever. And that the friction must have that same angle underneath the axes. So in reality, this should be drawn since friction acts specifically opposite. Question is, does the angle matter? Not really, right? Because our next thing is going to be F net. If we know that this is pulling in this direction, then we know that this must be the opposite direction. And that's really all we need to know for the F net equation that we're going for next. Okay? So the angle doesn't really matter, but the resultant magnitude does. Because now we're going to assume there is acceleration because we were asked to calculate the acceleration of the system. And what's the expression we can write for the only two forces we have? These two. R minus F. So now can we solve for acceleration?
Yeah.
Do we have the mass? Do we have the resultant? Do we have the friction? Yes. Do we care what direction friction is going? No. Do we care what direction resultant is going? No. Could I ask you that? Yeah, because you could solve for it. But in this particular problem, we want acceleration. That was the goal of the problem. Yay, Newton's law problems. They all come down to F net equals ma. You have a system that is moving and changing direction or changing speed, it is ma. If you have a system that is being constant, then F net equals 0. So someone get A for me and tell me what it is.
I got 0.21.
You got 0.2? Okay. That sounds about right. Should a child be moving any faster than that on a sled? Probably not. 0.2 what? Okay. Let's go back a little. Let's talk about your final exam. I'm gonna have you make your own study guide. I had you do this in the past before. You're gonna use the section goals from all the sections we've covered. You've done this before. Some of you have. Most of you have seen me do something along these lines before. If not, I'm gonna walk you through it either way. Okay? I want you to make it. You're gonna upload it to Canvas so I can see that you've done it. But I'm gonna show you where to find everything. There are 2 locations in which I would recommend you use. The learning objectives are in each individual section. We did do chapter 1 in the chapter. So you're going to do all of the sections in chapter 1. You're going to do all of the sections in chapter 2, kinematics. You're going to do all of section 3, so we did do all of section 3, and then you're going to do 4.1 through, technically we did do 6. Right, 6 was like problem-solving strategies, though. It wasn't like new information. It's like, how should we solve these types of problems? We're going to spend time this week solving more of the free body diagram type problems like this, because there are a lot of them, and because each of them is slightly different. So we want to be practicing how to use those skills before our final exam. Okay. Oh, I don't think this thing is on. Oh, this is going to be bad. Oh, man. Everybody pray for the computer.
Praying.
Do you know how much our final exam is going to be like weighted? Like, is it going to be 10% of
It's
our
the
grade?
same as 20.
Okay.
Yeah. But it is the last final exam for most of you, right? It's the last like final exams you have to take here. As long as you keep your grades up.
That's so exciting.
Don't know why I even have to say any of that. You have to have a B or higher.
Oh, really?
Yeah.
Well, sweet.
Well, that's definitely the wrong password, but okay. Whatever you want. All right. So, if you are not familiar with the OpenStax website, I don't know how that's even possible at this point, but if for some reason you have managed to never crack the textbook open this entire semester, and there is always one, you are looking for, under the Science tab, the book that says Physics for AP Courses. Then you're going to click View Online, and then you have this lovely table of contents. No, you don't need that. Okay. Leave me alone. Feel harassed. When you go to a section, oh my gosh, why is it like this? It's so annoying. Okay, when you go to a section at the very top, there is a thing that says Learning Objectives. Each individual section will have this gray box. It says Learning Objectives. You are to copy them down by section. So get a piece of paper out, write Section 1.1, Learning Objective 1, explain the difference between blah, 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 and blah, blah, blah. Okay? Your goal is to make yourself the list and then go through the list and cross off the things you're good with. If you already know the difference between a principle and a law or a model and a theory, which I hope you are okay on that end, if you're not, do a quick read. But if you're good with that one, you just check it off. I recommend making a checkbox, right? Like I like to do checkboxes. Tick box. Explain. Then when you feel good about it, you exit off. Okay? I want you to do that for all of the chapters up through 4.6. And we have covered every section from section 1 of chapter 1 through section 6 of chapter 4. Okay? Go ahead and get started. You got 5 minutes. Don't waste your time. Find the book. Just find the book for me. Like, just do that at least. Like, open it up on a tab and then forget about it.
Like, why don't they want to connect the book? They're like one.
They're absolutely charged. Or they're same charge to me. If you flip it around, it'll connect.
Oh, like here? What the?
They're,
What?
it's like, you know, like a north and a south end of a magnet. North and north don't want anything to do with each other, but north and south do.
That's so weird. I did not know that.
Oh, look.
So this one, okay, so I gotta go here.
This is your book. This is the gray box. These are the objectives that I want you to write up. Okay? Have a great day.